Much earlier in this chapter, I teased the idea of atoms of the same element having a different number of neutrons, having different masses. We're going to talk about that now. So, isotopes are elements that have the same number of protons, which means they're the same element, but they have different numbers of neutrons. Now, when we're comparing one isotope to another, so for example, comparing chlorine 35 to chlorine 37, chemically speaking, they are practically identical. Technically, they're a teeny tiny bit different, but for everyday chemistry, there's no way you're ever going to be able to tell the difference from one isotope to another. That is the truth in the majority of cases. There are a few cases that are an exception to that, especially in the really heavy elements, and these would be things like uranium, plutonium, thorium, thallium, really big elements where one isotope is radioactive compared to a different isotope that is not nearly as radioactive. So in those cases, there is actually a chemical difference. But for the vast majority, especially with the smaller elements, you're never going to be able to tell the difference from one isotope to another. When we are trying to describe one isotope versus another using the chemical symbol, the way we're going to do that is using the mass number. So if we're looking at an elemental symbol, this is a generic one here. We've already talked about this main part in the middle here. That's just the symbol from the periodic table. So for carbon, this would be C. We've already talked about this up here. This is the net charge. So if something has a charge of -2, you would put 2 minus up here. Down here in the bottom left, if you want, you can put the atomic number. Which is, again, just the number of protons in that element. The vast majority of the time, it's not necessary, though, because if you know what element you have, you also know how many protons. So you can put it there, but you don't have to most of the time. Up here, in the top left, is where we're going to put the mass number. And the mass number is what's going to allow us to tell the difference between one isotope and another. This mass number is the number of protons plus the number of neutrons. It's just the protons and the neutrons added together. That's all it is. So if you have carbon 12, for example, which I think we're going to see on the next page. Actually, why don't we just go ahead and look at it? Actually, we don't have it there. Okay, I thought we were going to have it. So carbon 12, for example, that is telling us that the protons and neutrons added together is equal to 12. Well, we know, or if you would know if you looked at the periodic table, that carbon has 6 protons. So if we know we have 6 protons, and we know we have a mass number of 12, that then allows us to solve for the number of neutrons, which must be 6. Because that's the only thing that gives us 12 here. So let's do something similar here. We are going to work out for these 9 different isotopes how many protons, neutrons, and electrons we have in each of these. So let's go ahead and just do it row by row. So let's do the top row first. And I think I'll do the top row with you, and then the second and third row I'll ask you to do on your own. I guess technically if you wanted to, you could pause the video now and try to do the top row, but I won't ask you to do it. So this first one here is just plain old magnesium. We're trying to determine protons, neutrons, and electrons. So if we look up magnesium on the periodic table, magnesium is element number 12. We're not told that this has a charge. If we have nothing here, then we assume that it's net neutral. And what that means is not that we have 0 electrons. That means we have the same number of electrons as protons. That gives us the neutral charge, having the same number. Not having none, having the same number. So then the last part here is the number of neutrons. Now we're not given a mass number here, and so to get the number of neutrons, I'm just going to take the number, the mass number from the periodic table and round it to the nearest whole number. So that would be 24. So if we have 24 as our mass number, and we have 12 protons, that means we must have 12 neutrons. Because again, the mass number is protons and neutrons added together, which would give us 24. For the next one here, it's similar in that we're not given a mass number or a charge, which tells us that we have a net neutral charge. So we have 26 protons with iron, which means we must have 26 electrons. And then the number of neutrons, if I check the periodic table, iron is closest to 56, which would mean that I have 30 neutrons. Because the neutrons and protons added together is 56. I already know that I have to have 26 protons, so if I subtract the protons from the mass number, what I'm left with is the number of neutrons, which is 30. So then the last one here on this top group, oxygen is element number 8. I'm not given a charge, so I'm going to assume that I have the same number of electrons as protons, but I am given a mass number this time. And so I'm not just going to look at the periodic table, I'm going to use the mass number to determine the number of neutrons. I have 15 for the mass number, 8 protons in the element, which leaves me with 7 neutrons. Okay, I hope that makes sense. Why don't you try the next 3 here? Try to work those out. These are a little bit tougher than the first 3, but you can solve them exactly the same way that we did the first 3. So go ahead and give those a try. Okay. First one here, lithium, the lightest metal in the universe. Only 3 protons. We're not given any information on the mass number, but if you check the periodic table, it has a mass number of 7, which means it would have 4 neutrons to give it its total of 7 for its mass number. And we have a charge of +1, which means we have 1 fewer electron than proton, giving us 2. Aluminum 3+, kind of similar. No mass number given, but if we check the periodic table, aluminum is element number 13. It has a mass number of, it's closest to 27, which would give us 14 for the number of neutrons. And then the number of electrons would be 10, because we have 3 more protons than electrons, hence the +3 charge. And the last one here on this row, it's our first one to give us both a mass number and a charge. So the number of protons here is 17, again from the periodic table. So if we have 17 protons and a mass number of 37, that means we must have 20 neutrons. And because we have a charge of -1, that tells us we have one more electron than proton, which would be 18. Alright, last group here. So go ahead and pause the video one more time. Try to work out those last 3 symbols. Okay. So we have sulfur as our first one there. Sulfur is element number 16, which means it has 16 protons. We're not given a mass number, but if we look at the periodic table, it's 32 is the closest integer to the mass number, which would mean that the number of neutrons is also 16. For the charge, we're told that we have -2, which means we have 2 more electrons than protons, which gives us 18. For the uranium, this one is a big one. It is element number 92. And we are told that 232 is its mass number, which means that we have 140 neutrons. That is a whole bunch of neutrons. But that is the way things work, which we'll talk about in a later chapter. As you get to really large elements, you tend to have a lot more neutrons than protons. And we'll talk about why that's the case later. And then the last thing here, 92 electrons, because we have the same number of protons as electrons because there is no net charge. So the last symbol here is just hydrogen, which is element number 1. There's no charge given, so it would have 1 electron as well. If you look at the periodic table, it has a mass number of 1, which then makes it tempting to say that you have 1 neutron. But you actually have 0. Because if you have a mass number of 1, and the mass number is the protons and neutrons added together, you can't have a neutron if you already have the 1 proton. And so, in reality, the vast majority of hydrogen actually does not have any neutrons. It is just the 1 proton. Alright. Hopefully that makes sense. Hopefully you were able to work through at least the majority of those and get those correct. In the next and last video in this chapter, we will talk about the atomic weights on the periodic table and how they are a bit strange given our definition of a mass number. So I'll see you there.